Hi everybody, let's talk about the trapezoid rule. This is a procedure for estimating the area under a curve in case the calculus problem is too difficult to solve. So how does it work? You start by chopping your interval. Say we're trying to estimate this area. We'll chop that into a certain number of pieces. Here I've drawn 4 pieces. On each piece, you measure the function height at both ends, and then you draw a straight line connecting those 2 points. These are trapezoids, and so you then estimate the area of the original function by adding up. You can compute these 4 trapezoid areas exactly and add those up, and that would give you an estimate. In this picture, our function was concave up, and you can see that the straight lines that we've drawn in between the points at the ends are above the original function's graph. So we're going to get a slight overestimate for the area under this curve using the trapezoid rule. And that would be true even if you did 100 intervals instead of 4. What if your function is concave down? If you do a similar idea, connecting pairs of points with a straight line, you will get an underestimate for the correct area of the function. Okay. If your function graph happens to be a straight line, then you're in luck because the trapezoid rule will perfectly give you the correct area under the curve. But that's the best possible situation. Although if your function really is a straight line, you don't need a numerical estimate for it. You don't need to program a computer. That's a solvable problem. But it is important to note that the error that the trapezoid makes is related to the size of the second derivative. So if your second derivative were really tiny, then you would expect the trapezoid rule to do a good job. There's a theorem that makes all of that more clear, which I've written out here. So what's going on here? We're going to estimate this integral using a trapezoid rule. We're going to split it into n subintervals. So n was 4 in the picture I drew above. And then this is an important sentence. If the second derivative of f never gets larger than m in absolute value between x equals a and x equals b, okay, so m is the maximum value of second derivative of f on the interval you're integrating, then the error of the trapezoid rule is at most this number. So what's going on there? We've got number of subintervals, maximum value of second derivative, distance from the start to the end of the interval we're integrating, and a 12. So that's a guarantee. One thing to notice is that e is small if n is big or m is small. Both of those things make sense. If you're using lots of rectangles, you'll get a more accurate answer. If your second derivative is very close to 0, then your function is almost a straight line, so you'll expect an accurate estimate. Another thing to note, what happens if you use twice as many subintervals? So instead of n, you're going to use 2n. What would that do to e? It's going to mean that e should be cut by a factor of 4. So you do twice as much work, but you get 4 times as accurate an answer. And the other thing to notice here is that f needs to actually have a second derivative. If f has some funny behavior with non-differentiable points, then this theorem doesn't apply. But that's the guarantee of accuracy of the trapezoid rule.